The goal of this talk is to introduce what are some of the statistical challenges that we have on banking, more specifically related to data science, which essentially is machine learning plus computer science, like having stuff in production, making so that it takes decision real time. So exactly how do we apply data science in banking, and why banking is such a fascinating industry? So I'll go over, like, this is the main goal of this talk. A little bit about me. I graduated in economics, so I'm not a very good program. I program by necessity, but my background is in economics and statistics and stuff like that. I joined Nubank to work in credit, but I quickly moved to marketing. And at some point I moved to collections. And collection is just like, people don't pay their credit card. You have to understand how to make they pay their credit card. And at that point in my career, I mostly worked as a data engineering, like trying to get all the data pipelines to work and how to make sure that the decisions we wanted to take were actually being made. And this was very tough, but it taught me a little bit about programming. At this point, I became a manager because the bank was growing too much and we needed managers to lead the new folks. Didn't like that too much, so I stayed as a manager for 2 years. I became a manager, and now I'm working as like a full individual contributor, and I'm mostly a causal inference specialist inside the bank. Today, I work mostly with credit, although I serve as an internal consultant for multiple areas. Like I advise people in marketing, I advise people in debit, and all other sorts of areas for the bank. A bank is a very big, complex company and has a very interesting challenges, but I'm focusing on only one, which is the main challenge here. Otherwise, we won't have time. In fact, I have, I think, 45 slides. So I'll have to go at a rate of about 1 slide per minute. I think I can do that, and so that I can cover all that I want to cover today. So we'll focus mostly on the credit card business, our credit card. And in order to do that, I first want to make you understand what exactly is the credit card business. And I know you're all like, again, to just be clear, I don't mean to disrespect the intelligence of anyone here, but I think it's very useful for us to go back to very first principle, because it's going to be important later on the talk. So the first thing we need to understand about a bank is the economics of credit card. So the first things first, like how does a bank lose money? Like, this is very important. And essentially how a bank loses money is that at the end of every month, a customer has a decision. The customer can pay the credit card bill, or it cannot pay the credit card bill. And if somehow the customer chooses to not pay the credit card bill, that's how the bank loses money. So we give money to people and they don't pay us back. So this is a major way of, or the way that banks lose money. And we can model that pretty simply, like the loss, like the amount of money that the bank loses is simply the amount of money we give plus the probability of someone not paying back that loan. So if we chart this like money on the y-axis and credit line on the x-axis, we'll get a pretty straight line, which essentially is like the probability of someone defaulting times the amount of money that we give. So this is one part of the equation, which is how we lose money, like what's the loss part. We also have to look at the gain part. And again, there is other components here, but one way that a bank gets money, at least on credit card, is what is called interchange. So every transaction that someone's made, for instance, let's say that you want to use swipe your credit card to buy a concert ticket. And on that transaction, the bank is going to get a very small percentage of that transaction, like 0.005%, something very small, and that goes to the bank. So this is another major source of revenue. So this is a major source of revenue for credit cards. There's also interest. We'll not talk about interest today for the sake of time, but interest is also a very interesting problem. Today we're only going to talk about interchange. So if we chart this on the same plot, what we have is that the amount of money that the bank makes is simply how much customers spend which is a function of credit line, times a very small, a very small number, what is called the interchange rate. And this function, it is concave because if we give a lot of credit to a customer, at some point the customer will not want to spend more. Like the customer is satisfied at some point, so it doesn't matter. Like if you give him, I don't know, $100,000 of credit line, he will not spend 100,000. This spend will saturate at some point. Okay, so we have these two curves. We have the revenues and we have the cost curve. And the goal, like the business that I want to talk about, is how do we decide how much money to give to the customer? And there's nothing very fancy here if we think about it. Like, again, just to be clear, this is a simplification of the problem. Like the function of the firm is much more complicated than that, but this is a very simplification that paints a neat picture that already can like translate 80% of the problem. So again, not to go very fancy, how we optimize credit line is essentially very similar. Like it's economics 101. We essentially ask questions about marginal revenues and marginal costs. For instance, let's say we want to understand, should we give $1,000 of credit line? We see, okay, what's the extra cost I'm going to have by offering $1,000? So this is this very small amount, but the extra revenues is much higher. So I'm going to gain much more than I'm going to lose if I give 1,000. So I can make this decision. And I keep asking this question. So, okay, but why not 2,000? What happens if I give 2,000? So I make the same question again and say, okay, if I move from 1,000 to 2,000, I have, again, a small extra cost and a very huge extra gain. So it makes sense to make this move. At some point, it won't make sense anymore. We see that the extra cost is actually bigger than the extra revenue, so I don't make this move, which means that the optimal line is somewhere around here. And again, this is nothing fancy. I don't want to offend the intelligence of anyone. It's essentially just showing that it's very basic, but it will imply in a bunch of other things that I'm going to show later in the talk. So for folks that have some familiarity with economics, this is essentially setting marginal revenues equal to marginal costs. This is a very basic firm optimization problem. And if we take the functions that we defined before, like we can open this function. So the cost function, like we said, is just credit line times risk. So the derivative of this function is just risk. Like if we differentiate the cost side with respect to credit line, we just get risk. On the other side, if we differentiate the revenue curve with respect to credit line, we get the interchange rate plus the derivative of the spend function with respect to credit line. This is going to be a problem in the end because we don't know how this function behaves, and it's going to be very important to estimate this function here. So from this, I hope it already is starting to become clear what the bank needs to do in order to decide credit lines. First, let's look at the revenue, the cost side. Okay, so this is underwriting. So this is basically why banks stress a lot about underwriting, is because the risk component is key in the optimization process of lines. Like we said, we need to find this in order to solve this equation. So we need an estimate for risk. And an estimate for risk is just something that estimates if a customer is going to default on their credit card or not. So you might look at this and say, okay, this is something I know of. Like I can use whatever fancy deep machine learning model comes to your mind, like it can be logistic regression, neural network, like GBM, whatever, anything that takes customer features and predict credit default. So this is a very traditional, or let's say, textbook example of supervised machine learning, right? Like super easy. I can do that with my eyes closed. Anyone can do that. Why it's so hard then to give credit to people? And yeah, in some aspect, it is super easy. Like you have a target, which is a binary target, default or not, and a bunch of features like credit scores from credit bureaus, like FICO score and stuff like that. And you want to predict if a customer is going to default given those features. But the hard part of the problem is not building the model, actually, something else entirely. For instance, one of the biggest challenges that we have is actually defining what is the outcome variable. Like, what is your y here? Like, what are exactly you predicting? And to give an example of how that decision can be made, one thing that we need to consider, there are other things, but this is one thing that we need to consider, is how long do we wait until we classify a customer as a 1, a default, or as a 0, as a non-default. So for instance, we might be willing to wait 2 months since the customer gets a credit card. So we give a credit card to the customer, and we wait 2 months, and we say, okay, did this customer paid bill 1 and bill 2? If so, it's a good customer. If not, it's a bad customer. We classify as a default. The problem here is that the customer might not pay in the 3rd bill, or in the 4th bill, or in the 6th bill. So we have this trade-off between waiting more time to see if the customer is going to default or not, or waiting less time to see if a customer is going to default or not. And the trade-off is that if we wait too much, like the more we wait, the more certain we are about the quality of the customer. But the downside is that we have to wait a lot. And this is the problem. For instance, if we have a 6-month window, we'll have to wait 6 months, like a batch of customer joins your bank, and you cannot retrain your model with that batch of customers. You have to wait 6 months until you throw that data into your model to estimate the risk or to re-estimate your model. Because you have to wait until the target or the outcome variable, what we call mature, like you can observe, like it's not the moment the customer gets in the bank, you still don't get to see if it's a 0, if it's a 1, you have to wait a long time. So this is the trade-off, like, do we wait a lot and then we have to rely on very old data to predict new customer behavior? Or do we wait very little, but then we might have a noisy target, like the customer might default after we classify it as a default or not. And again, why is this a problem? Is because let's say that you define your window as 6 months, you can only use very old cohorts. A cohort here is meaning a batch of customers that joined your bank. So you can only use very old cohorts to train your model. And let's say that you have a situation like this, right? So this plot shows essentially percentage of customers late. So this is what you want to minimize. This is bad. Like as this goal, this is essentially risk, like how the average default rate. And on the x-axis, you have month since the customer joined the bank. So let's say that the topmost line here is a customer that joined the bank 8 months ago. And you get to see if those customers defaulted or not if you're using a target window of 6 months. But the newer cohort, it seems that the risk of the newer cohorts are decreasing. So if you have to rely on very old data to retrain your model, it's going to be very hard to predict what is the risk of the early and newer cohorts. And if this is not stationary, like if risk increases and decreases, this becomes a problem. So if you looked at a problem like this before, it probably recognizes this is very similar, or it is what we call a survival analysis, right? So in this case, like if we cut a window of 6 months, we have to wait until 6 months to say if a customer defaulted, and it means that we have to drop all the data prior to reaching 6 months. Or we can use some other techniques of survival analysis to leverage all the data, and that becomes way more interesting way to model this thing. So the second problem of why it's not so trivial to just build a machine model and call it a day, so it's the problem of selection bias. And afterwards, I'm going to merge the problem of a long-term or censored target with the problem of selection bias to see why it becomes a little bit of a challenge. So if you think about it, how are you going to use your machine learning model? So you're going to build a model that predicts risk, and you're going to use that model as a filter. So you're going to give credit to people that have low risk, and you're not going to give credit to people that have high risk. So your machine learning model essentially works as a filter between people that want credit and people that actually got credit. And if you think about it, where do you actually get to see the outcome variable? Where do you actually get to estimate your model? Well, of course, you have to estimate your model on the people that your previous models approved. You do not know the risk of customers that you have not given credit card for, right? That you have not given credit for. So you only know the risk of customers that you've given credit to. However, your interest, you want your model to perform well on people that you have not given credit to. You want to know if your model is going to be better at underwriting new people, not the ones that you already have. So this creates a mismatch between where you're estimating your model and where you're applying or where you're making predictions for your model. And this is essentially the problem of selection bias. Essentially, there's a distribution shift or a population shift between where the model is estimated and where the model makes predictions. And here is like some of the difference that we have is between these two populations is that the population where the model wants to be used for, the model wants to make prediction on people that apply for credit. And these people that apply for credit are usually riskier than the ones that got approved for credit. The population that apply for credit is riskier, but also more stable. I'm going to get that in a moment, and also more heterogeneous. While the people that you have, the people that got credit, is less risky, is more unstable, and the reason for that, for why it is unstable, is because as the bank increases its risk appetite or decreases its risk appetite, the population that comes in can shift the risk. Like the bank, what the bank does, if the bank allows more people in, the risk is going to increase. If the bank allows less people to get in, the risk is going to decrease. So this population here is susceptible to internal shocks, to shocks of the decision that the bank itself make, while the people that actually want credit are not susceptible to that sort of shock. They have some shock, like for instance, if a pandemic comes up, of course, risk of the entire market is going to shift. But if the bank makes a decision, the risk of the entire market is not going to shift. So again, just for clarity, the default probability of people that want credit is much higher than the default probability of people that got credit. And this creates a mismatch. Like your average risk prediction from your model is going to be lower than your risk prediction for where you're going to make predictions. So you have to make some sort of adjustment for that. Another very interesting phenomenon happens when you shift between models. So let's say that you have a very good model making predictions and approving people for credit, but now you've estimated a new model, and this model is even better than the old very good model. And you want to put that model in production. But the moment you want to put the model in production, you also want to, you want to make sure that this new model you're putting in production is in fact better than the old model that is already in production. And ideally, what you see is something like this, like the risk of the customer is high, and as you put a better model in production, the risk should decrease. So the model is able to better select between less riskier people and more riskier people. So that's ideally what you want to see. Like, as you put a new model in production, the model classifies people better and it reduces the risk of people approved for credit. However, there's a very interesting phenomenon that happens here. So for instance, let's say that you have a new model. So you are developing a new model, which is this blue model here. And you are evaluating this model in terms of ROC AUC. So for those that don't know what ROC AUC means, it's just you want to know if the model classifies between people that have ones and zeros. So ROC AUC essentially orders rank order people between people that have ones and people that have zero, and the better the ordering between people that have ones and zero, the better the model is. So and this is essentially a metric that tells how good your model is at predicting zeros and ones. So let's say that you build a very good model, which is this blue model, and you did everything correct. You did cross validation, you validate everything, there's no leakage, everything is perfect. And you're certain that this model is better than your old model, so you want to put it in production. However, the moment you put it in production, you see the performance of the model degrades. And even more troublesome, it seems that if you compare the new model with the old model, which is, let's say it's the orange one, the new model is better across the training period, across the validation period, but as soon as you put the new model in production, the new model degrades and the old model becomes a little bit better. And you look at this and you think, okay, what's wrong? Like, did I do something wrong? Is the production environment not correct? And it's nothing of the sort. It's just a nature of the data. So just the nature of the problem make this happen. And if you think about it, let's see how the two models, like if you think about what the models are doing, let's say that you have the old model, which is the purple one. So the purple one is saying, okay, I'm saying that everything inside the circle are low risk. So I'm going to approve all these customers here. And this model says, okay, I have these people, and the people that the old model selected are the ones where you are validating the new model. So the new model, what's the data that you're using to validate the new model is the data that was approved by the old model, right? So you get to validate the new model on the data that the old model approved. However, once you shift that, so once you put a new model in production and the new model starts to make decision, what will happen is that now you're validating in production, you're validating the new model on the data that it approved. And of course, this model is going to be a little bit worse on itself because you're validating the model on the mistakes that it makes. Like, think about it. You're using a model to let people in your bank. You're using the model to say, okay, these people have low risk. If they have low risk, I'm going to let them in. But of course, this model is not perfect. Like, it makes mistakes. And the people that default that the model let in, but actually were bad customers, they're going to show up only after you put that model in production. So what essentially happened is that you're now validating the model on the mistakes that it makes. So as soon as you put a model in production, the data that you have are going to be data that passes through that model, and hence you only see data that it mistakes. So in this example here, for instance, the new model, the blue one, it can classify between low-risk customers and high-risk customers much better. Like, it produces more complicated surface, it classifies better. So it has very little customers that default and don't default. However, everything that it misclassifies now becomes the data that we have to validate it. So the model has to, how we compute the AUC, we're now computing the AUC on this data set here, which essentially has only the mistakes from this model. Another thing that we can think about is that if we go back here, the percentage of risk is decreasing over time, right? So as we improve the model, there are less and less ones on the data set. So the data set becomes more and more unbalanced. It has lower and lower people with ones classified. Ideally, right? Like, if we're getting better and better at saying that people have high risk and low risk, we want the risk over time to decrease. And essentially what happened is that as you transition from one model to another, you want the data set to become more and more unbalanced. For instance, at the old model, the purple one, we had way more high-risk people. And at the new model, we have very little high-risk people. And also, this only phenomenon can make the AUC go down because it essentially means that the task is harder. Like, You want only to classify. The data set becomes harder and harder and harder as you only leave people that have very low risk on the data set. So if you combine these two problems, the fact that the internal data where you can validate your model, or the data where you can actually see the outcome variable, is constantly changing by new models you put in production. Like if the bank is more or less aggressive, for instance, if let's say that the bank is less conservative, so it's letting riskier people in, the moment the bank lets more riskier people in, the model will get better because it becomes easier to classify between high risk and low risk people. Like if you have a bunch of examples of high risk people, it suddenly becomes easier to separate them. So an internal policy like this, like letting more people in, might make your metric, your valuation metric go up. And something like you deploy a new model in production might make your valuation metric go down. And something completely external, like a pandemic, can make your metric go down even more. So all of this makes it very hard for you to decide, okay, is this model really good, or is this model really better or than the old one? Like the AUC seems to be going all over the place. So how do you actually validate this model is very, very tough. I can't exactly answer how to solve this problem, but it seems like I can give a hint. It seems that all of this stems from the problem of this mismatch here. Like the people that get credit is fundamentally different from the people that apply for credit. If you can somehow get a sample or a representative sample of people that apply for credit, then you might be able to understand how your model performs on it. So for instance, you can do something, okay, let's just approve randomly some people and see how the model performs on that set of people that are randomly approved and not subjected to any crazy things or crazy policies from the bank. So this is like sort of a hint on how to actually solve this problem, but this is the root of the problem comes from here. The fact that where you're estimating your model and where you're validating your model is a population that, one, keeps shifting and is fundamentally different from the population that you actually care about. So this is one very tough problem of this business, the banking business. So yeah, of course, some of it is just machine learning, fit a model. But also it's very hard to understand how to validate that model, how to make the model generalize to the place that you want if the data keeps changing and if the data is fundamentally different from where you estimate and where you make predictions. Pair this with the fact that targets are long-term, like we said before. So if targets are long-term, it means that you have to use past data or very old data to predict future behavior. And in the presence of non-stationary, this just adds complexity to the problem. So if things were pristine and stationary, it would be okay for you to use very old data. But if things keep changing all of the time, ideally you want to use data that is as recent as possible. I'm going to pause here before I go to the next section, which is to talk about the revenues part, because I know this is a lot of stuff and just want to see if there's any questions for this section. Or should I just like continue and leave all the questions?
There's one brief question from Thomas in the chat, which I can read out. So I'm curious if banks are using alternative credit products, example, secured CCs, very low limit cards, etc., to help evaluate those folks who would have otherwise been not approved.
So secured loans, right? Something to use secured loan, right?
Credit cards.
Yeah. Yeah, that's a very good point. Like for instance, what secured loans are is that you can you might not be able to approve these people with a credit card, but you might be able to approve them if they give a collateral. So if they deposit something on your bank and leave that as a collateral, you can give them a credit card. The issue is that these are fundamentally different dynamics, right? The moment you ask for a collateral, you actually decrease the risk of the population. So you change, by doing that, you essentially change the risk of a population. So a same customer with a collateral is way less riskier than a customer without a collateral. So you cannot essentially validate your risk model on customer with a collateral and expect it to predict well the risk of people without collateral. So that's again very different business, and it will not have. You might solve the issue of distribution shifts on, let's say, your X variables, right? Like they have the same features. Let's say you can sample the features from them, but the relationship between X and Y will be fundamentally different on people that have collateral and people that don't have collateral. Okay, so let's go back to the beginning of the presentation. Is essentially where essentially is told, okay, this is what we're trying to solve. We want to find the derivative of costs and make it equal to the derivative of revenues. The derivative of cost is risk, which is very nice because risk is something that you can observe. Like you can see if a people defaulted or not. Of course, there are some, it's not trivial to define what a default is, but it's essentially an observed thing. Like it's a Y variable that you can plug a 1 or a 0 to each individual in your database. The other part is a little bit trickier, is that on the revenue side, what you want to know is the derivative of the spend curve, of the spend with respect to credit line. And this is way trickier because you cannot actually see this derivative. I'm going to go there in a moment, but the point is that one thing that I want to get out of the way is that notice that what I care about is not spend itself. I don't really want to predict spend. For instance, let's say if you look at the right part of the slide, you can see two spend curves, one which is shifted up and one which is below. Doesn't matter if my spend is shifted up or down. If the slope is the same, I'm going to have the exact same optimal point. What is going to define the optimal point here is only the slope of the spend curve. Okay? So for the same risk curve, for the same red curve, what will define my optimal line is how steep the spend curve is. For instance, if the spend curve is very flat, like here on the left, I'll probably have a very low optimal line. But if the spend curve is very steep, I'm probably going to have a very high optimal credit line. So what I care about here is not spend to predict spend. What I really care about is to predict the derivative of spend with respect to credit line. And this is tough because you cannot, like, you can definitely see how much a customer spent, but you cannot see the derivative of this curve. And this is essentially a causal inference problem, or if some folks already, I don't know if you're familiar with causal inference, but the problem is essentially that you cannot see the same customer at different points on the credit line curve. Like you only get to see the customer at a single point in this curve, so there is no way for you to estimate the derivative or for you to see the derivative of a curve, which is very tough because, again, you want to predict the derivative of the spend curve for each customer that comes to your account, but that's not something you can observe. So you're essentially estimating something that you cannot observe, which is derivatives. There's also a problem with bias. So let's say that you have data on spend and credit line, and the true relationship between credit line and spend looks something like this purple line. However, it's very common for the bank to give more credit line to people that are less risky. And for the same credit line, people that have less risk, they spend less. So this adds bias to your data set. You're essentially giving more lines to people that will spend less. So the data looks with a slope much lower than the true one that you want to estimate. So we have to deal with that. So let's say that somehow you deal with the fact that credit lines are not randomly assigned, which causes bias on your data set. And somehow you manage to figure that out. So you can understand the average relationship between spend and credit line, or you can estimate an average derivative of spend with respect to credit line. Still, this is not actually what is more interesting, because we don't really care about the average here. Like, we're not particularly interested in how sensitive the entire market is to credit line. We essentially want to classify people between more sensitive and less sensitive to credit lines. So this is what we call a treatment effect heterogeneity problem, or a CAT, a problem of conditional average treatment effect estimation. So essentially what we want to do is we want to find the derivative of spend with respect to credit line for each segment of people, right? And the reason for that is it stems from the optimization problem. We want to find people that have very steep spend curve and people that have very flat spend curves. And this will allow us to give high limits and low limits. This is a very tough problem for some reasons, right? First, most of the causal inference literature deals with binary treatment. So a binary treatment, let's say that we only have two credit lines, 1,000 and 3,000, then we have a binary treatment. It's either like treatment or control, and then you can estimate the derivative just doing average spend at the treatment minus average spend at the control divided by 2,000. So you can estimate this line here with 2 points. So, and this would give you the treatment effect from going from 1,000 to 3,000. However, this is not the case with credit line, because credit line is actually a continuous treatment. And the literature on continuous treatment is very limited and not as well developed as the literature on binary treatment. But still, like, let's say, okay, it's not so different. You might be willing to say, okay, I'm going to summarize, or I'm going to estimate the derivative of spend with respect to credit line by simply fitting a regression line. So I'll fit a regression line of spend on credit line, and I'm going to extract the slope of this parameter, and I'm going to say that the slope of the curve that I estimated will function as the derivative that I want to estimate, right? It seems very reasonable. It's not that simple, because like we mentioned before, this relation is not linear, which means that the slope changes as we change the treatment. So at higher credit lines, we're going to have a less steep derivative. At lower credit line, you're going to have a higher derivative. So how do you deal with that? It becomes an entirely different matter. So remember that the goal here is to classify people between more sensitive and less sensitive to credit lines. And this might come in two flavors. For instance, you might have these two sorts of people. Okay, so let's say that you can classify people between more sensitive, which are the red customers, and classify people between less sensitive, which is the orange customer. In this situation, you're actually classifying the entire curve. So the entire curve, we were saying, okay, this customer that has this entire curve is more sensitive, and this other type of customer that has this entire curve is less sensitive to credit line. Which is very hard, because you have to separate the entire curve between one and the other type of customer. Another way to classify sensitivity is that you can actually use where the customer are on the curve. Like, if you are at the beginning of the curve, I'm going to say that you have a high sensitivity. If you are at the end of the curve, I'm going to say that you have a low sensitivity. So this will essentially like split the problem in half and estimate local derivative depending on where you are on the credit line. Which of these approaches you're going to use to say if people are more or less sensitive to credit lines depends a lot on the business that you're trying to solve. For instance, if you want to give the first credit line, if these are new customers, you cannot use local derivative because people are nowhere in this curve. Like, they have zero credit line. They are here, like they're at the beginning of the curve, and you want to understand which credit line to give to them. So there is no running from this. You have to estimate the entire curve, and you have to say, okay, this type of customer here has this type of curve, and that other type of customer here that has this type of curve there. While if you have a problem where someone is already a customer and you want to give them a credit line increase. So they are in this curve. So let's say someone has a credit line of 1,000 and you want to give them an increase. You can focus only on the small portion of the curve, only on around 1,000, and that makes the problem a lot more tractable because you don't have to estimate the entire curve. You only have to estimate a local derivative. And all of this, again, all of this is just because we want to separate people between more and less sensitive to spend, which again simply stems from what I've talked very early in the conversation, that this is a problem, this is a problem of the firm. You just have to solve this problem. You just have to equate the derivative of loss with the derivative of revenues. And all of those causal inference hardship comes from the fact that you need to estimate the slope of the spend curve, which will dictate essentially where exactly do you want to set your credit line? Is it higher or lower? So I guess this is what I had to talk about the problem of banking. Again, this is a very small scope of the banking problem. It's just how do you decide your credit line? And from solving a problem of the firm, which says that marginal revenues equals marginal costs, and that gets you to first have to estimate marginal cost, which is just risk, and then you have to estimate marginal revenues, which is much more troublesome because it's a causal objective, and you get into all those complexities of causal inference on that side. But once you do that, then you just equate one with another, and it will magically give you an optimal line. So this is, again, very broad simplification of the problem, but this is how a problem of optimizing credit lines might be designed.
Thank you very much. I'll stop recording.